This is the two-sample t-test. This is when, instead of just comparing one sample against a number or a claim, we're going to compare two samples against each other. So let's find an example. The juniors and seniors compete to see who has the better average on stats tests. The 10 juniors had an average of 34.0 points with a standard deviation of 3.9, and the 14 seniors had an average of 32.1 points with a standard deviation of 5.2. Is this difference statistically significant? So what this test will do is tell us if these two numbers are just different by coincidence, the given day, a little bit of randomness of who our sample was, or is it actually statistically meaningful that we have a difference of 1.9 points. So let's go ahead and calculate that using our two-sample t-test. Our null hypothesis is that they are the same. Whenever we're dealing with two samples, the null is always that these two are equal to each other. The alternative is that one of them is larger than the other or that they're not equal. In this case, we're just trying to see if the difference is significant. We're not saying that juniors or seniors are better than the other, although you may have an opinion about that. So we're going to do a not equals test. As far as collecting our numbers, we have a whole bunch of them in here. We have 10 juniors. That's how many we have in our first sample. We have an average of 34 points. That's our x-bar in our first sample. And then we have a standard deviation of 3.9. So that's our standard deviation here. So let's go ahead and uncover these here. 34, 3.9, and 10. We got that from the context of the problem. Next part, we have 14 seniors. That's the number of seniors. So that's our second value of n. We have an average of 32.1 points. So that's our sample data collected, our x-bar. And we have a standard deviation of 5.2. So that's going to be our SX2 here. So we'll uncover these. Now, it does not make a difference which one you pick to be 1 and which one you pick to be 2. I typically pick 1 to be the first one I read in the problem. So if I read about the juniors first, I decided to make them sample 1. If there's another logical way that you keep track of things, that's fine. It really doesn't make a difference as long as you are consistent with how you write your hypotheses. If you think the seniors are greater and the seniors were sample 1, then you would say sample 1 was greater. It would be flipped if it was the other way around. The key is that as long as you're consistent, 1 and 2 doesn't make a difference. So let's take out our calculators and see how to do this. To start out, we're going to go to the stat key as always. We're going to go over to our tests, and we want to choose a two-sample t-test. Two-samp t-test. That's the fourth one down. So we select that. This time we're dealing with statistics. We have a list of numbers that we're going to enter, not a, well, I guess a list of statistics, not a set of raw data. So we're going to choose the stats option. And then we have this x1, sx1, n1, and those are the numbers that we found in the problem that we highlighted above. So conveniently they're in a nice order here. So we have our 34.0 for our x1, x bar 1. Our sx is going to be 3.9. And then our sample size will be 10. For sample 2 here, x bar is 32.1. We have a 5.2 standard deviation and a sample size of 14. Finally, our alternative hypothesis, we said that mu1 is not equal to mu2, so that will be just selecting that. So we'll choose the first option for not equals. Pooled, that's just a technique of calculating the standard deviation differently. We're not going to discuss that much in here, so you can ignore that and just leave that as no for now. And then we calculate. We get out a p-value, just like always. We also get some t-statistics. We have df, which is degrees of freedom. And then you have the original numbers that you typed in, and it'll give those back to you again, just so you have them. But the p-value is the main thing that we're looking for here. So as far as if things are statistically significant, this is what we care about. Like most scenarios, we're going to choose the alpha value of 0.05. This is definitely larger than 0.05, so what we have concluded is that there is statistically no significant difference between the scores of the juniors and the scores of the seniors. It's just coincidence or the sample that we chose. Next example is the exact same test, the exact same calculator function, except this time, instead of being given a list of stats, we have raw numbers, and the calculator will take care of figuring out the stats for the juniors and the seniors. So same basic starting point. Juniors and seniors compete to see who has the better average. The data is below. Is it statistically significant? The null is that they are equal to each other. That's always going to be the null hypothesis. The alternative is that they are not equal. We don't know which one's going to be better. We don't have a guess of, oh, seniors must be better because they're seniors. We're just going to say they're not equal. So now let's go back to our calculators and punch in our list of numbers. We go to Stat, we go to Edit like usual. And unlike the first example where we only use L1, this time we're going to use L1 and we're going to use L2. Decided to make the juniors L1. They're right here on top. So I start typing these in. I'll pause the video and let you finish that yourself. Once you finish the first list, you can hop over to the second list and start typing in these values here. And don't miss these values here at the end that I had covered up a moment ago, so make sure you get those last values there for the seniors. Once you have your list 1 and list 2 all filled up, we're going to go back to the stat key again. We're going to go again over to tests, again down to 2 SampTTest, just like we did a moment ago. And this time we're going to choose data as our input. We're going to select to input real data. That data, the first list is going to come from list 1, the second list from list 2, so we'll leave those. Our frequencies will both be 1, we'll never change that. Our alternative hypothesis, we're saying not equal. We chose not equal, so we'll leave that set on not equal there. Leave pooled to no, and then we'll calculate. Again, we get our p-value back. That's the number we care about. In this set of data, it looks like we had a little bit better luck as far as finding a difference between them, but our p-value, 0.14, is still larger than 0.05 by quite a bit. So we cannot conclude that juniors and seniors are truly different, that there is a statistically significant difference in their scores. We would say that we cannot reject the null hypothesis, that they are in fact equal, and that on any given day you're just going to get some variation.